What we're going to talk about today is the summary of curve sketching. So actually today we'll have almost nothing to do with it. What it will have though is it will have us graphing curves, graphing some kind of graph that we're going to do. The goal is to do it without this, which is going to be brutal hard. Right? It's like, well, I spent $100 and something, I should be able to use this, right? Unfortunately, the math guys think that we did it before these were made, so you should have to do it.
Well, we were smarter than that.
Yeah, exactly. See?
We're smart enough to make it.
So we will be able to. I mean, my only issue, my only worry is when we eventually take that test, half of it is no calculator, literally half. So you're gonna have to be able to analytically think about some kind of graph and be able to, do some stuff with it, yada yada, without using one of these fancy dance calculators. So that's my only saving grace. Is we eventually have to get back to that, no matter what. So.
Half the chemistry test is like without a calculator, and they make you like times decimals, and we were all like, crap, how do you do this?
They made you do that.
So there's big things that we want to check for. There's big things we want to check for as far as when we sketch graphs. Okay, so we're going to be sketching graphs, and once again we're sketching, so they don't have to be perfect, but they want to be close. They want to be close to what they would actually be if we were to graph them, or at least have a general idea. Okay. As far as the summary goes, there's a whole list of things that we want to be searching for when we go ahead and do these graphs. Okay, and we're just going to kind of run through the list. The first big things I think are going to be the domain would be a first good one to check. Find out the possible x values that we can even plug in, right? Which we'll get to in a little bit. Range is also a nice possible value, but I kind of saved the range for some other stuff. But domain's a good thing to find. Intercepts are a good thing to find. And that's like x-intercepts and y-intercepts. Those are always good things. Asymptotes are always good. And that kind of goes along with domain a little bit for some of them, right? The vertical asymptotes happen at the domain restrictions unless there's holes and whatnot. Horizontal asymptotes happen at the infinity stuff that we've been doing the last couple of days. So we're hopefully are okay on that. For polynomials, we want to know what the ends of the polynomials are doing. Are they going up to infinity or down to negative infinity? Who knows what they're doing? But the asymptote idea is kind of the general idea. What's the far right and far left sides of the graph doing? And then let's see, make sure I'm not missing anything. All right, so then we got the dirty stuff, the stuff that we've been doing. Our derivative, our second derivative. Derivative tells us where possible max and mins are, tells us the slope, tells us increasing and decreasing, tells us a whole bunch of stuff, and we set up intervals based on that. Okay. From this first derivative, we ended up getting critical numbers. Okay, where we set that first derivative equal to 0 or undefined. Those are the two things we look for there. And the second derivative, we talked about inflection points. Okay, we talked about inflection points, and once again, that's where it equals 0 or undefined. So one of those two. You just set it there.
Okay.
And these are kind of the big ones. This also tells us concavity, tells us if it's concave up, concave down. Inflection points tells us where it switches from concave up to concave down, and so on and so forth. Okay, so this is kind of the stuff I want to run through when I'm looking at graphs and I'm trying to figure out what a graph is actually going to look like. Okay, so I want to just run through some of that real quick. Let's go ahead and start out pretty basic. We'll start out with, I think polynomials are a little bit easier. So on your homework tonight, I think the polynomials, they actually put them at the end, but I think it might be easier to do them at the beginning. And the reason I say that is because the derivatives are a lot easier to find. So in my opinion, they're a little bit easier, but kind of up to you. Okay, now on all this stuff, the things that we want to find, I always think it's good to get the derivatives out of the way first. So go ahead and find the first derivative, find the second derivative, and just have those at the top, and we'll be using those to plug in kind of as we go. Okay, so the first derivative for this one should be pretty easy. We got 4x to the third, we got minus 36x squared, and then plus 8096x, and then minus 64.
Did you say 8096?
80. I was doubling the 4 for 80, and then
say, like, that's a
carrying the 1, 90, and then say, yeah. Sorry, it's how I do it in my head.
Okay.
And that's my first derivative, and then I want to find the second derivative, so let's go ahead and find that real quick. So second derivative is going to be at, 12x squared, and then minus 72, so I think it's 72x, and then plus 96 for my second derivative. Okay, so are we feeling pretty good about those so far? Okay, now what I want to do is I kind of want to run through that little list of stuff. Okay, so I want to first find out what the domain is. Okay, so what would our domain for this one be? What can I plug in for my x values? Any restrictions? Anything I can't put, yeah, nothing I can't really worry about. So all real numbers for that. So I can plug in any number. That means that I'm going to have some kind of continuous graph all the way across. Okay, there's no holes or gaps or anything like that. Okay, domains, all real numbers. Intercepts are a good thing to find, I think. Intercept would include x-intercepts and y-intercepts. Okay, if I were to find an x-intercept, I plug a 0 in for y. If I want to find a y-intercept, I plug a 0 in for x. Okay. So I think the the y-intercepts are by far easier to do, right? If I plug in a 0 for my x values, that gives me my y-intercept. So if I plug in a 0, I just get 0. So 0, 0 is a y-intercept. It's also an x-intercept as well. Okay, yeah.
If you plugged in 0, wouldn't you still have like 64? Oh, wait. Going to the original? Okay.
Yeah, it's kind of tough to figure out which one you're going to plug it into, okay, but try to keep those organized on which one you're actually looking at, okay? I plugged in a 0 in my original function, and that got me 0, so that's where the 0, 0 came from, okay? Now, if I want to find the x-intercept, I'm going to plug a 0 in for y, which f of x is y, so I have to solve for where 0 equals x to the 4th minus 12x to the 3rd plus 48x squared minus 64x. Okay, so I have to solve for that, which is going to be a little bit challenging, but we'll be able to figure it out. Okay, well, the first one, I can just factor a common factor of an x out of all those, right? So if I took an x out of all of those, I'm just going to take an x out of all of those right now. Is that okay?
Yes.
Finger math. I'm going to be starving for room in a moment, so I'm trying to cheat a little bit. You guys have lots of paper there. Okay, so now I'm going to solve for this. Now, technically, I have an x sitting in the front for the factor, right? But what would make that 0? 0. So I already have that point, though, right? So I don't need to put that one again. So now I'm just looking for where this guy equals 0. Can we factor that? I don't know if this one, I don't think this one factors very clean. Maybe. If you have 4 terms, usually you would think of splitting or grouping it, right? I think that would be the best way to do it. Does that split or group, though, very well? I kind of don't think it's going to very well. So then your other option here is that rational root test, which is kind of big and nasty. I'm going to just cheat and tell you that one of the zeros is going to be 4 on this one. Just trying to cheat and help you out. So I'm going to synthetically divide 4 in there and just see what's left over. So if I divide a 4 in there,
And how do we do the other?
you find the possible factors of 64. So like 1, 2, 4, plus or minus all those. 1, 2, 4, 12. The big list of numbers, right? And you just guess and check, basically synthetically divide there. Now, please don't. There's not going to be a lot of that, so don't waste your time on that. Okay, there's not going to be that much of that as far as next homework goes. Okay, you'll either be able to factor it or do something different. Okay, but I'm just telling you this is one option for how to solve this. Okay, so I get a 1, a negative 12, a 48, and a negative 64. And so if I just synthetically divide that, 1 and 4 and negative 8 and negative 32. Screw that up? No, I'm good. 16, 64, that's 0. Cool. So 4 works, which is good. So 4 works, that's one of them. And then I have the leftover here, which is x squared minus 8x plus 16, which actually I can factor that guy as well to x minus 4 and x minus 4. And so then 4s would be my other answers there. So I actually have 4 that happens 3 times there. So 4 is my other x-intercept. Okay? Or, I'm sorry, other y-intercept. So 4 is the one that's going to work. So I'd put a 4 right here. 4 is going to be my intercept. They're probably going to be a little easier than that one, but I like this problem. I didn't want to do a different one. All right, anyway, so those are my 2 intercepts right here. And so if I were to graph it, I know I have 2 actual points on the graph in which I can graph it. That means that my graph right here at 1, 2, 3, 4, I have a point, 4, 0, and I have a point at 0, 0. So I know I've got 2 points right there right away. Okay? So that's what the intercepts do for you, to give you a rough guideline for how tall, how high the graph is, and whatnot, and you're good to go from there. Okay? All right, so that's the intercepts. Okay, let's go ahead and see what else I need. I need asymptotes. Okay, let me erase this now. I need asymptotes. Okay, what kind of asymptotes do I have on my original function right here? None. I have none, right? No horizontal, no vertical. If the domain's all real numbers, I won't have any vertical asymptotes. Horizontal is happen at the fractions, the rational ones is what they call them, so when you have some kind of fraction. And then the slants also happen there as well. So I've got no asymptotes for this particular one, which is kind of nice. It means I'm going to be continuous all the way through here. No holes or gaps or lines or nothing to worry about there. Okay? I'm just running through my little rap sheet. Now let's go ahead and do the first derivative and set that equal to 0. Okay, I want to find out where the first derivative equals 0. So I'm going to set the f prime of x equal to 0, which would equal this 4x to the third minus 36x squared plus 96x, and then minus 60. So now I'd like to solve for that guy if I can. So I'd factor 4 out all those again. All right, so let's go ahead and divide everything by a 4. So what do you get here? You get the 0 would equal x to the third, because I think 4 goes in all of those, right? Yeah. 4 goes in that, what, 9 times? So minus 9x squared. Looks pretty good. 4 out of 96. 24, okay. 24x, and then 4 out of that minus 16. Once again, I don't know if that one factors by grouping very nicely. Kind of gross. So I'm going to guess another number. 4 is a good guess. I think 4 works. Oh, 4 didn't work.
Why is it?
4 should have worked there, I thought.
Yeah, why -1?
Why did you get the -1?
Oh, yeah, because I'm retarded. Thank you. I was like, gosh, I knew it worked when I did it earlier. It didn't work. All right, cool. So that means that 4 is going to be a critical number, okay, or a possible critical number, possible spot where the derivative equals 0. Okay, and I have some other ones in here, right? I've got some other ones I've got. So let's see, this is x squared minus 5x plus 4 equals 0, so I can factor that guy. That'd be x minus 4, x minus 1, I believe. So that means 4 and 1 are my other ones. So my 2 critical numbers here are going to be at 1 and 4. Those are going to be my 2 critical numbers. Okay, we okay with that? It's not too bad. Now what does that mean? I got 4 and 1. Those are my critical numbers. What does that tell me? Could be max or min. Okay, it doesn't have to be, but could be max or min at 1 or 4. Okay, those are the spots where it could be a maximum min. Okay, so 4 and 1, so I'm going to erase this stuff now. So I got my critical numbers. Okay, so I'm going to put critical numbers, and these are possible critical numbers at 1 and 4. Okay, let's go ahead and find inflection points now. Okay, and that's where the second derivative equals 0. That's where the second derivative equals 0, which is this guy right here. So I have second derivative equals 0. So as far as my inflection points go, I'm going to set this 12x squared minus 72x plus 96. I'm going to set that equal to 0. Try to solve for that. Does 12 go into... Yeah. Okay, 12 goes into all of those, so I'm going to divide a 12 out of those. So x squared, 12 out of that goes in there 6 times. Yep. Minus 6x, and then 12 goes out of 96 8 times. Okay. Now I can factor that, so I factor the x plus... No, x minus 4, x minus 2. So then 4 and then 2 are my possible inflection points. Okay, so I got possible inflection points that are going to be at 4 and 2. Okay? All right, we feeling pretty good about that? Now, just by looking at a couple results for what I've done so far, if I have a critical number and the inflection point are the same right there, that's kind of like that second derivative test, right? I found a critical point. If my second derivative at that point equals 0, that means I don't know if it's a max or min. So I'm pretty much just assuming that this 4 is not going to be a max or min. Okay? So we can, this point right here, not going to be a max or min. Doesn't mean this one couldn't be, or something else in between them. Which would be at 1 would be the other spot where it could potentially be. What's that?
Why can't 4 be?
Because the second derivative test says if I find my critical numbers, right, and I plug those into the second derivative, if that equals 0, then that test failed, right? So if I plug in a 4 into the second derivative right there, I know I got 0 because it's an inflection point, so I know that I'm done there. Okay? Yeah.
So like when you do the factoring stuff and factor out a number, why don't you like use that at all?
Oh, because let me factor it out. If I put a 12 out here and a 12 out here, and that equals 0, what does that do to the equation? As far as finding zeros, nothing really, right? Because you could just literally divide both sides by 12 there. I'm just saying effectively we don't really need it. So you could leave it there though. That's fine if you did. And they'd probably get mad if you just made it go away. But in my mind, it's just gone. It doesn't do anything as far as that goes. Okay. All right, cool. So we got a whole bunch of stuff, and now I want to figure out. Now I want to set up kind of some test intervals, and the intervals I want to set them up around are my critical points and my inflection points. Okay, that's where stuff is changing. So I want to set up some intervals based on 1, 2, and 4. Okay, so if I look at 1, 2, and 4, I want to set up my intervals for that. Okay, so my first interval, I'm going to go from negative infinity to what was my first one? 1. So negative infinity to 1 is going to be my first interval point. Okay, and then I've got a point that's x equals 1. I'm going to show you just a table strategy that the book uses. You might like it, you might hate it. Who knows? We'll find out. Okay, and then my next interval is from 1 to 2, it looks like. So 1 to 2. Next value is, because 2 is an inflection point, so stuff might change between those. I'm just looking up at all the intervals I could possibly look at. Okay, so I've got x is 1. I went from 1 to 2. X is 2 now. Find out what the things going on there. And then we're going to go from 2 to 4. And then I'm going to go x is 4. And then I'm going to go from 4 to infinity.
I didn't know you involved the inflection points too.
Yeah.
With the critical.
Because what does that do when I set up my intervals based on that? What happens there? For your second derivative. I haven't done anything yet. Don't freak out yet. It'll all make sense in a moment. And this is probably overkill for a lot of the stuff you're going to do, but I'm just showing it to you, okay? These right here are my intervals and my possible points, which you can also, I guess you can think of as intervals, 1 to 1. Okay, then I want to find out some f of x function, the derivative function, the second derivative function, and the conclusion. I think we used a different word there, but I don't care. We're going to use conclusion. Just have faith for a moment. Have faith for a moment. It'll all become clear. And this is probably a bit of overkill, but that's okay. Overkill is good every once in a while.
I just have a question.
It's a block day, so we have lots of time. Yeah.
In general, because I was gone, right? Why are we doing this?
Why are we doing? Oh, because a lot of the stuff. This is going to hopefully cement all of our stuff that we've done so far. This is all a summary of what we've done, so nothing here should be really new, which is kind of nice.
Okay.
We're just piling it all together now, and we're trying to graph without using this fancy tool.
Oh,
Because
okay.
unfortunately, on that stinking test, they're going to take it away from you for half the time. So
Okay.
we have to be able to think about graphs and how they work and all the stuff that we've learned. Okay. Anyways, so I want to think about the interval from negative infinity to 1. Okay, that for on my graph, negative infinity to 1. I want to think about the interval, and whenever you're thinking about an interval, you're not really concerned about the actual function here. All you know that is this guy's continuous on this interval right here. It's going to be a smooth curve all the way through. Okay. Now, if I go to my first derivative, I want to pick a point in this interval and figure out if the first derivative is positive or negative, because that tells me a fair amount. Okay. So if I pick a number between negative infinity and 0, and I figure out if that's going to be a positive or a negative number on my first derivative function, right? So what number can I plug in this interval right here? 0. Okay, plug in 0 into the first derivative, which we have right there, right? So what do I get if I plug in 0 for the first derivative right here?
Negative.
A negative number. That's all I care about is sign. Okay, all I care about is that's a negative number. That's all that matters. Okay. Now I'm going to go to my second derivative and plug in a number between negative infinity and 1. 0, right? Obviously. Plug in 0 to the second derivative. What's that tell you? Positive. Okay, so this is a positive number. Okay, so I've got a negative and a positive. Now, just by laying it out in this fashion, right, I've got the first derivative as a negative number. What does that tell me if the first derivative is negative on this interval right here?
It's decreasing.
It tells you decreasing. Perfect. It tells you the slope is going down. It tells you it's a decreasing function. Okay, so I know I'm going downhill, left to right, downhill from negative infinity all the way to 1. I'm decreasing on that range. Okay. Now, what about my second derivative? Second derivative is positive. So what's that tell me? Concave up. Good. I'm just going to put concave up. See you. Okay, so I know it's decreasing, and I know it's concave up. Okay, so from the interval, so that tells me just on my graph right here, I'm not going to graph the whole thing, but on the interval from negative infinity to 1 right here, I'm going to be decreasing, going downhill, plus I have this point. I'm going downhill, and I'm concave up, which means it's going to look something like that on that little range. Okay, that's what I know so far. Ballpark. Okay. Now I want to look at the value right at x equals 1. Okay, well, right at x equals 1, let's find out what happens at these guys right here. Okay, so what's my value at x equals 1 on the function? If you were to plug in a 1 right there into my original function, what's the value give you? No, I actually want a value on this one. I don't want positive or negative. This one's an actual point that I'll end up graphing.
Negative 36.
Negative 36? It's not negative 36.
Negative 28.
It's got to be odd.
Yeah.
It's got to be an odd number.
First derivative.
No, in the function. I'm just saying it's got to be an odd number. Negative 27, that sounds about right. Okay, so negative 27. So I've got the value is negative 27. Okay, now I want to plug that into the first derivative. Okay, so I'm going to plug 1 into the first derivative. Well, wait a second. What's 1 going to be in the first derivative? It's a critical number, so the value is 0. Okay, it was a critical number.
Wait, why don't you care about the sign for that one? Why do you
I do care about the sign, but what's the sign for 0?
Yeah.
Trick question. There isn't one, right? Okay, so that one I'm just going to put a 0 in there for that.
It's like if it was a normal number, you put the sign.
If a normal number, I put the sign. But if it was, then you didn't pick the right interval, probably.
Oh,
Is my guess.
Yeah.
Maybe. But I would just put the sign. It might for the second derivative, though. Like, what's the second derivative if I plug in a 1 for the second derivative? 1, so I get 24. Positive? I think so. I think it's positive. Okay, so we'll get back to the conclusion in a moment. Let's fill out the rest of this stuff and see what we get.
How come between the interval and the first on the original equation?
We don't really know what that is, though. It's not.
If I plugged in.
It could be positive or negative. We don't really know, right? So we don't really know based on the original equation yet.
But how does it not know?
Because what value would you plug in there? If you plug it, this is an interval. It's not a specific point, right? The first derivative and the second derivative guarantee me that I'm either increasing all the way through or decreasing or concave up, concave down. But on an interval of the function, it could be above the graph or below the graph. Who knows? You know, so we can't really draw a conclusion based on that box. So I just leave it blank on that one, to be honest with you.
Okay, so for the derivative of x or whatever, do you plug like a point or whatever into that equation?
Yep.
Okay.
Yep. So now I'm going to pick from 1 to 2, right? Pick a number between 1 and 2. So 3 halves, 1.5, 1.5, right? Plug 1.5 in it's not going to be very nice. We're going to leave that blank. Okay? On the interval 1 to 2 is not a specific point. Okay, what about the first derivative? Plug in 1.5 on the first derivative real quick. You're not very nice. And you can't use a calculator. You can for this. I don't mind if you use a calculator, just know that you have to be able to do it without it. Yeah. I'll just plug in a 1.5.
Where are you supposed to do that?
You just do it in your head.
Oh, I erased the second derivative. I didn't mean to do that.
What is it the first one? Going to be positive.
Somebody else did that on the calculator already, I'm sure. So this is 27,
No, actually,
1.5,
Do like general idea.
27 eighths, 4, so half is 27. 14, 13 and a half. Maybe. 13.5. Yeah, where's Sherman when I need him, huh? 9, 4, 9 is 81, so that's 81. If that's 48, so that's a positive, really big number. Anybody actually get it? Is it positive or negative?
Positive 12.5.
I hope it's fine. I'm just trusting you guys. Now, it doesn't bother me if it were me, what I'd probably end up doing is putting the three functions, the function, the first derivative, second derivative, just put them in your y equals, and then be checking values that way. Okay, just to save you guys some time. Okay, they'll probably make the graphs a little easier, but save yourselves a little bit of time there. Okay, so 1 and 2. So between the 1 and 2 interval, 1.5, plug in the second derivative. Anybody get that one? By chance? No. 1.5. Okay. Positive?
I don't know.
It's definitely positive.
Definitely positive. Okay.
No.
Where's negative?
Yeah.
It has to be
It
positive.
doesn't have to.
I erased
It's
my
positive.
second derivative.
Scott, you didn't have to do anything. You can do whatever.
Okay. So, now, based on this, right? Based on this, I've got the first derivative is 0, and I've got concave up, right? I know it's concave up.
And it's increasing.
And no, it's not increasing or decreasing. Slope is 0, right? So if it's concave up, right, and the slope is 0, right, what would this point be?
It's the relative.
It's a relative minimum. Good. That's got to be a minimum point.
Why is it
How can you tell?
Because second derivative is concave up, so I know my graph is going to go like this, and my first derivative slope is 0. So if my slope is 0, and my concave is going up, then I can tell that that's a minimum point. Okay? So I know that's going to be a minimum point. So I know that at the point, 1, negative 27, 1, negative 27, like right here, that's a minimum point. So now my graph is getting a little clearer. It's going through this point, and it's going to be concave up and then decreasing through that same. So it's going to swing up here, hopefully. Looks like it's concave up right here on the interval from 1 to 2, and it's increasing. So I'm going to go increasing and concave up. Okay, so once I hit this, I'm going to go back to increasing. I'm going to stay concave up so it doesn't switch over to concave down or anything like that, which we kind of knew that was going to happen. Okay, plug in the value of 2. See what the value of 2 is in the function. Okay, and once again, I would just put those in your graphs. So, negative 16? Really? Okay. So at 2, we're at negative 16. So that means I got a graph at 2, negative 16. So it's like right here. Okay, and then at 2, what happens at 2? I erased all my stuff there. Sorry. But what happens if I plug in 2 to the first derivative?
Positive.
Positive? Okay, so positive. Tells me it's increasing still. Second derivative, I think this was an inflection point if I remember right. So I think this guy was 0. Okay, so this guy means that we have an inflection point. Maybe. I don't know if I want to write the inflection point yet. But I know that I'm increasing. I know that much so far. Okay, now I want to do the interval from 2 to 4. So plug in 3. Alright, so if I plug in a 3 into the, I'm going to leave that guy blank, plug in 3 into the first derivative, find out if it's positive or negative. It's probably positive. That's my guess. Second derivative, I'm guessing second derivative is negative.
Yep.
Just guessing because I think I know what the graph looks like. Yeah, I know. Now this one I'm increasing still, so I'm still increasing. Notice here on this, I can call this now an inflection point because I've switched from concave up to concave down right here. And so now I can actually call this an inflection point. So this is an inflection point here. And here I know this is concave down. Because I switched from concavity right here, that's got to be an inflection point. Okay, so I've got an inflection point. I'm increasing, and I'm concave down, which means I switched at this point right here, and now it's going to curve something like this. Okay, so now I've got that curve. Oh, sorry. So I went concave down. I went decreasing, concave up, increasing. Hit my inflection point, concave down, still increasing. Okay, what about the value of 4? I know 4 is 0, right? If I plug in a 4. 4 on my first derivative, was 4 a inflection point? Or I'm sorry, a critical number, so that was 0. So technically not a critical number there. And then x is 4, let's see, plug in 4 to the second derivative. I think I also got 0 for that guy, right? So that means this guy's nothing. Right? I'm not decreasing anymore right at the point of 4. Right? So that means right at 3, 4, that means it's going to hit that point right here. Like so. Right at the value of 4. From 2 all the way to 4, I knew it was increasing, and then I knew I was increasing and then concave down, so that got me to there. And then I know the point crosses right there at 4, 0. Now let's do 4 to infinity, so like plug in a 5, let's say, right? So if I plug in a 5, let's see, plug in a 5, well I can't really do that one. Positive, positive? Positive, positive, which means it's increasing, and it's going to switch to concave up. So right here, this is going to switch like so, and it's probably going to go up forever like that. And I went from a negative concavity to a positive concavity, right? Concave down to concave up. It's concave up, which means this guy was an inflection point. So I've got an inflection point. It was not a critical number, though. Okay? No max or no min on that. Okay. Oh, and this one's also increased. We got one problem done.
Yes.
Can we use our calculators a little bit now?
Yeah.
Please. Now, just keep in mind, you use your calculators for like maybe the road math, just plugging in numbers and whatnot, and be smart about that. But you still want to be thinking about this stuff as you go. Okay. All right, let's go ahead and do one more, or maybe three more. We'll see. We got lots of time. Yeah, well, we got lots of time. Oh, it didn't take that long. We started late.
That's what happened.
32. One down, 3 to go. Actually, 2 to go. I do want to do 2 more probably.
You just did the math for us.
Yeah.
You're welcome. Like I said, sometimes this table is overkill for some people. They don't like doing quite this much.
What do you?
Some people try to do a lot of this in their head without like actually writing the table down. But the table kind of helps you see a little bit. We're going to try to save the conclusions for the end, although I think you guys might be able to figure some of that out. So let's go ahead and grind through the math real quick. Now for this one, I want to kind of go back to that same thing. First off, I want to think about my domain for this guy, right? So domain would be all real numbers. Not equal to 2. You guys okay with that? I think. So I'm kind of running through this rap sheet. Now the only catch is be careful with that. Maybe this numerator factors. Can we factor the numerator? Doesn't hurt to look, because if it cancels with the x minus 2, I'd have a hole, which would change an asymptote. Okay, but I don't think I can factor that numerator, right? Okay, so my domain's all real numbers not equal to 2. Okay, what was the next thing we wanted to find? Intercepts? Yes. Right, those would be a good thing to find. Okay, let's find our intercepts. And the intercepts I would find a 0 and a 0. Those are the big things to find. You might have multiple ones, but that's how I always start. Okay, so if I plug a 0 in for x, that's a pretty easy one usually, right? Plug a 0 in for x, what do you get? No?
-2.
-2. Okay, plug in a 0, you get -2. Okay, now I want to set it equal to 0 and try to figure out where this equation equals 0. Right, that'll find my other intercept for me. So on that one, effectively, I got to set the numerator equal to 0. Right? Because the 0 over whatever is going to be 0. So I want to solve for where that guy equals 0. Ooh, it didn't factor. Did it not factor very nicely? Is that guy going to not have any zeros? I kind of have a feeling it's not going to have any zeros. Let me throw it on my graph real quick, even though I'm not supposed to do that. I would do quadratic formula, but in the interest of time. Okay, so I got that. So no zeros on that one. You guys okay with that? So this one didn't work. Gone. We okay there? All right, cool. So intercepts are good. I got the domain. I got the intercepts. What about asymptotes? I should have something here, right? What kind of asymptote am I going to have here?
Vertical.
Vertical. Okay, vertical asymptote at 2 at x equals 2. Okay, that's pretty good. X equals 2. I'm going to have a vertical asymptote. Sounds pretty good. Do I have any horizontal asymptotes here? Nothing horizontal, right? The power's bigger on top, right? From our limits from before. So if it's bigger on top, it doesn't have a horizontal asymptote. Now, it doesn't have a horizontal asymptote. However, it does have, I don't know if you guys remember, it has a slant asymptote.
Yeah.
Nope.
We'll come back to that later. Okay, let's not get bogged down on that right now. Okay, so we got a vertical asymptote right there. We do have a slant asymptote, which I'll come back and tell you about that in a second. Okay, so that's what we got so far. Man. My eyes going crazy. Okay, it was a little off. Okay, cool. So now we've got that. Let's go ahead and find. We got our derivatives, right? Let's go ahead and find our critical numbers. Okay, critical numbers are where this guy equals 0. Okay, where our first derivative equals 0, which is 0 and 4. Okay, anywhere else?
So
What about 2?
undefined.
It's undefined 2. Yep. Could be because undefined just means it's not differentiable. It could have like a sharp turn or something like that. However, we know it's going to be an asymptote right here, so we pretty much know what's going on there. Okay, but 0, 4, and 2 are possible critical numbers. We pretty much are going to put a star by this one. We know that one's not going to be a maximum in because that one doesn't even fit in the domain, right? So we obviously can't have a maximum or minimum there. Okay. What about our inflection numbers? Any spot where that equals 0 undefined? 2 again, right? So 2 is another possible point of inflection. Okay? So point of inflection possibly can happen at 2 when we're all said and done with it. Okay? Alright, so that's cool. So let's go ahead and set up our intervals based on this. Okay, going from, yeah.
But isn't the domain like not, can't use 2? Can't be 2?
The domain is, you can't use 2. You're exactly right.
So why those?
Because they're possible inflection points, which means it could switch there. Okay? Now remember, these are derivatives, okay? Or second derivatives. The derivatives might not be differentiable. That doesn't mean that 2 couldn't work on the original equation. Okay? Every once in a while that happens, usually with like a rational exponent type problem is when you bump into that. Okay? So let's go ahead and take a look at this. I've got a vertical asymptote of x equals 2. Let's go ahead and set up my intervals real quick like. So for my interval for this one, I would go from negative infinity to 0 as my first one. And then I would plug in x equals 2. Find out what some values are there, which we're not going to be able to do. Okay, go from 2 to 4. That'll be my next interval. And then go x equals 4. And then go from 4 to infinity.
You just skip 0.
Why did I skip 0? Yeah, because I'm retarded.
Okay.
That's fine. 0. Oh, I meant to put 0 there. That's why. Okay. Yeah. 0 to 2. I saw the 2 and just ran with it. Sorry. X equals 2, and then I went from 2 to 4, and then I went x is 4, and then I went from 4 to infinity. Okay. So those are the big intervals that I want to check. Okay. So on this one, let's go ahead and just type in our functions on the calculator just so we have them. It'll just make solving them just a little easier. So, does somebody want to just do the second derivative and then hook me up with values on that?
Have all.
You've already got them in there?
Yeah.
Okay, so we're going to use and abuse you. Okay?
Wow. Yeah.
I know. Rockstar. It's good. So I got negative infinity to 0. Obviously, I can't do a function value at that interval. Okay, so let's pick a point like the first derivative. Plug in a negative 1. Okay, so we want to plug in a negative 1 into the first derivative.
It's graphing. Hang on.
It's negative? Thank you. Just go to your table. Can you just go to your table?
Yeah. It's all set up wrong.
There's your table.
Carl's going to do this. Okay.
Okay, so if I plug in a negative 1, I get a negative, and what do I get for second derivative? Negative. Okay, so let's not do conclusions yet. Let's just get the signs all figured out. Okay.
Don't we have to make the top equal 0 of the derivative? First derivative?
I did. That's where I got 0 and 4 from.
Right, so if I did a negative 1 there and I got a 5.
Did you plug it in the bottom too?
Oh, see, that's why.
It should still. Actually, it should be positive. Isn't
It's
this
positive.
That's what I thought.
Okay.
Positive.
Okay. Man, I should be typing these on my calculator. Yeah, that's got to be positive. What about negative 1 in here would be negative. That one is negative. I'm okay there. Okay. All right, let's plug in a 0. If I plug in a 0, I think I already plugged in a 0. 0 got me negative 2, I believe. So I know that value is negative 2. And I've got the first derivative. Plugging in the 0 into the first derivative gives me 0. Okay, plugging in a 0 into the second derivative gives me
2.
a negative number.
No.
Yeah, you.
What? plugging in 0.
I'm not even doing it on the calculator. I'm just doing it on this. If I plug in a 0 there, it's -2 cubed is -8. That's a negative number. Yeah.
Negative number, yeah, you're right.
Okay. So go pick a number between 0 and 2. Okay. So that's 1. I shouldn't trust you guys like that. So a 1 is going to be a negative, looks like. And a 1 down here is going to be a negative as well. I think, double check me as we go here. Okay.
I'm getting the exact opposite.
Okay, let's plug in a 2. Now, 2 is an actual value that I want to find. So 2 would be undefined. Okay, so undefined. Okay, and that's our asymptote. 2 into the first derivative is going to give me undefined again. Okay, 2 into the bottom one, undefined. Undefined conclusion. Good. Not a defined conclusion. Okay, 2 to 4, I'll pick 3. Okay, so 3 in the first derivative. 3 would be, let's see, a negative and then a negative, looks like. A 3 in the second derivative would be a positive. Plug in the value of a 4, which I think I can actually do that. Let's see, first derivative 4 is undefined. 4 down here is positive. What is it? 6? Okay, and then 4 to infinity, if I plug in a 5, let's see, a 5 is going to be positive for my first derivative, looks like, and a positive for my second derivative. Okay, this looks pretty good. So it looks like I'm concave down from negative infinity all the way to 2. So I'm concave down all the way from negative infinity to negative 2. That's good to know. Okay, so as far as my graph goes, if I've got a graph, I'm going to go out to 2, 1, 2, and I should have a vertical asymptote. So there's my vertical asymptote. I've got an actual value point at 0 and negative 2. Is that correct? 0 and negative 2. I have an actual point. Looks pretty good. I actually have another point here at 4, 6, don't I? So 3, 4, and then 1, 2, 3, 4, 5, 6. I've got a point right here. So I've got those 2 points right here. And I know from the left side, from in this area right here, I'm going to be, just from my graph right here, I've got concave down all the way through these, okay? So concave down, concave down, concave down, okay? It switches right here, but that doesn't mean we have an inflection point, okay? It switches, but it's not continuous. This is concave up, concave up, concave up. Okay? Now the graph right here is going to be increasing, okay? So we got increasing. Here the slope is 0.
So that's a minimum.
Maximum. So I have a relative maximum at 0, negative 2. So this right here is a relative maximum point. So that's the highest that graph's going to get, which means it's got to come in somewhere like that. Now I know I'm going to an asymptote, and I'm going negative and decreasing. I know this graph's going to go close to this asymptote, and that's a maximum, which means this graph's going to go something like this. Ballpark. About. Okay? Also notice that I'm concave down throughout that entire section right there, concave down. I'm increasing till I get to 0, and then I switch over, now I'm decreasing. Okay, so I'm decreasing right here. So that's why I went from a negative to a positive right here, increasing to decreasing, which also told me maximum. That's the first derivative. Okay, let's see, what else do we got? I got, once again, I'm decreasing right here, and I'm at concave down. Here I'm going to be decreasing and concave down. Here I'm 0, and I went from negative to a positive, so I went from decreasing to increasing, which makes it a minimum, or at the 0 it's concave up, which means it's going to be a minimum point. So that's a minimum point, and this one's also increasing. Which means this point right here is going to be a minimum value. I know it's going to go close to this asymptote, so it's going to go something like this. And if that's a minimum point, it's got to shoot up from there. So it's got to shoot up something like that. Okay, so my graph should look ballpark like that with all that calculus, which is sweetness. Okay. Does that table help a little bit? I know it's kind of a lot of work to do, but visually it might help people see kind of what's going on with these graphs, okay? So there's my graph. Now the crazy part is none of this is new. We've done all this stuff before. It's just a matter of putting it all together, and it makes for a long problem.
How do you find that?
Now, how do you find the slant? Because obviously it looks like there's a slant asymptote in here, right? The slant asymptote, you take the original function and you long divide it out, okay? So if I take 2 and synthetically divide that in there, it'd be a 1, a negative 2, and a 4. If I synthetically divide that, that gives me a 1, it gives me a 2, and a 0, and a 0, and a 4. Okay, now when we synthetically divide, we don't care about the remainder. All we care about is this right here, the constant. This is x. So y equals x is actually my slant asymptote for this guy right there. Okay, so that's how you would get the slant asymptote if you were to get one. Okay.
Wait.
So we take the domain can't be.
This was the original function, and I took what the domain can't be, whatever makes that 0, right? And I synthetically divided that, and the answer was my leftover. This is the remainder. Now the remainder we don't care about, okay? Because remember, asymptotes deal with the far right and the far left. So this plus 4 is going to do nothing to the equation, right? It's going to be gone. And effectively, what it really is, it's y equals x plus the remainder 4 over what we divided by x minus 2. But if you took the if you take the limit as x went really big here, that'd give you 0, right? So this is effectively gone. It's small potatoes. That's the big dog, okay? So y equals x is my slant asymptote for this one, okay? And you could obviously graph that, and you'd be good to go, okay? One more, and then we're done, okay? One more, I promise.
So for the slant asymptote,
You just divide them out. Longer synthetically divide. Yep. Trying to decide which one is more painful.
You pick the more painful.
how do you know why?
They get more painful? No, just can't throw me a cosine.
You had to put the
You're gonna like me after this problem.
How so? How so?
English paper.
This would take me forever to do.
Keep a topic calculator?
Well, square the not. Yeah, I would have taken. Now, obviously, you're kind of getting on borderline. You know, you're gonna need a calculator for some of these. Use your calculator. Just don't just what I'm trying to avoid you guys doing is literally hitting y equals, graph it, and then copy the graph and be done. That's what I'm trying to avoid. I know. Do a little work. It's good for you. Okay, it's good for you. Okay, so let's go ahead and run through that. You guys know a lot of calculator punching. We don't need a calculator for this stuff anymore. What's the domain for this one?
It can't be anything.
It can be anything? Yeah, it can be anything, right? There's no restrictions, right? I can plug in whatever number I want there, right? Now, typically, we have two things to worry about here. A fraction, we can't divide by 0. Is there anywhere where we're going to make that equal 0? No, never's going to equal 0. It's not going to happen. Okay? Anywhere where that's a negative number inside that square root.
Right, it's going to be positive.
It's always going to be positive, right? It's always going to square a negative number, positive. So my domain is all the numbers for that, which is nice. That means I have no vertical asymptotes, okay? So one of the asymptotes is gone already. Okay, what about my intercepts? Let's go ahead and do intercepts real quick here. I like to do 0 and something and 0. Those are my intercepts. Well, if I plug a 0 in there, for x I get 0. It's kind of nice. And if I set it equal to 0, the only spot where this function would equal 0 is where the numerator would equal 0, which is also at 0. Okay, so 0, 0 is my only intercept for this graph. Only spot where it crosses. That was a tricky one. Okay, now what about, let's see, what was the next thing on my list of asymptotes? Okay. I do have a horizontal asymptote here. You've got this one. You asked me about this one this morning. It is. Plus or minus 1. Technically plus or minus. Perfect. So we actually have two horizontal asymptotes. The reason is horizontal asymptotes, you look at the highest exponents that are there. This is x to the first power, and this is the square root of x to the second power. Now, if I were to ignore that plus 2 right there, the square root of x squared is x, right? And so it would be the same power, x over x. So you take the leading coefficients, which would be 1 over 1. That's bad math covering up that 2. Remember, when I plug in a bajillion, I don't care about plus 2. Okay, plus 2 does nothing to my bajillion. Okay? Okay. Hey, how many? If I had a nickel for every time Bill Gates said that, yeah, you'd probably give me a nickel. Yeah.
So in the last chapter that we learned about dividing powers and everything, we were really finding asymptotes.
Right. You were finding horizontal asymptotes. That's exactly what you were finding. Okay.
I thought they were intercepts.
How did I find what?
Well, they were limits.
The 1, because I took the coefficients. There's a 1 here and there's a 1 here, right? So I just divided those. Yep. So it's 1
Oh,
over
just,
1.
okay, coefficient.
Yep.
Okay, how do you tell where to look for a vertical or horizontal?
Vertical is a domain restriction. So vertical is if this said like not equal to 3, 3 would be a vertical, right? Or a whole, one of the two. You got to be a little bit careful on that. Anyways, one of the two. But if no restrictions there, so we don't have any vertical asymptotes to worry about. Okay. Horizontal happens. You look at it has to be a fraction. It has to be the powers that you're searching for. Okay.
What about slants?
Slant is it has to be bigger on top by a power of 1. And the reason for that is because when you long divide, if this power is bigger by 2, let's say, you'd get a parabola down here for your answer, and it wouldn't be a line. Which would be a weird thing to have. A parabolic asymptote. Talking fifth dimensions there. Yeah.
Okay, so for the asymptotes,
Yeah.
I see you were talking about the powers and everything. So
Yep.
what does that coefficient have to do with powers?
If it let's say this was a 5x to the second plus blah 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 blah
Yeah.
over 4x to the second plus blah 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 blah, right? You would just see that they're both x squared. You take 5 divided by 4,
Oh,
right?
so you just do the coefficients of that.
As long as they match, right? Which those match after I did the bad square root.
They don't match?
If it's bigger on top, and then it doesn't exist. If it's bigger on bottom, it's 0.
Oh.
All right, cool. So we're feeling pretty good about that, I hope. Okay, now what about, I'm sorry, next one on there was critical numbers, right? Okay, so what about critical number? Where does the first derivative equal 0? It doesn't, right? There's no critical numbers on this one, right? Okay, which is kind of nice because if there's no critical numbers, ooh, wait a second, that's weird. There's no critical numbers. That means we have no maxes. Doesn't mean it's a line. It means we have no max or no min. Okay, no maximum, no minimum value. It can't happen. Okay, so we know that no maximum, no min values. Okay, what about inflection points?
If there's no max, no min.
No, second derivative. Second derivative. We can still have concavity change though, right?
Right.
Okay. So where would my second derivative either equal 0 or undefined?
0.
0. Only spot, right? Anywhere where the bottom equals 0? Nope. Can never make that equal 0, right? I would get imaginary numbers. Okay, so that's pretty good, which is kind of nice. That means I only have one test interval section to do. Okay, so as far as my intervals go, intervals will be here. Okay, I'm going to run from negative infinity to 0. I'm going to look at 0, and then I'm going to go from 0 to infinity. I told you you'd like it.
They really, really like me.
For now.
Until I put the assignment up there.
Yep. And it's like 50 of these stupid problems that take half an hour.
That's right. You'll get faster at these and feel free to use your calculator.
It still is pretty long to do. Still takes me a long time.
It's still, yeah, it's kind of.
Okay, so I'm going to pick a number between 1 and 10. Between negative infinity and 0, so I'm going to pick like negative 1, right? Now I can't get a function, I can't get a value at some random number, but I can get the first derivative. Okay, so plug in a negative 1 into the first derivative. So negative 1 in here, is that going to be positive or negative? Positive, okay, so I'm going to get a positive value here. Plug in negative 1 in here, positive. Everybody okay with that? There's what? That's okay, but I plugged in negative 1. So it gave me a positive 6 over still. The denominator is always going to be positive, which is kind of nice. Did you notice that? No matter what the denominator is positive, doesn't matter what I plug in. Right? Okay, cool. Now what if I plug in the value x equals 0? If I plug in 0, I get 0. If I plug in 0 into the first derivative, right, I get a positive number. If I plug in 0 into the second derivative, 0 is going to give me a 0. No. Not test fails. No, not test fails. That's only if this equals 0 and this equals 0. Test fails. So, 0 to infinity, plug in a 1. Okay, I can't really plug in a 1 in the original function. I can plug in a 1 in the derivative. 1 would be positive, and a plug in a 1 would be negative, looks like. Okay. So I would say the conclusions for the end. It looks like, if you notice here, my graph is increasing on the whole thing. You guys okay with that? I'm increasing all the way throughout the entire thing. Here I'm going concave up, I switch right here, and I go concave down. So now I'm at concave down.
So 0 is an inflection.
And then 0 makes it an inflection point. Perfect. Okay? It's an inflection point because it's switched between positive and negative, concave up, concave down, and it's continuous. Okay? So, let's graph it. You guys have a general idea what it looks like? Maybe? Okay, my horizontal asymptotes are a positive 1 and a negative 1. Okay, the only intercept that I have is at 0, which is that point right there, at 0, 0. And I know from negative infinity to 0 here, I'm increasing, and I've got concave up. So if I'm going concave up, I have to be coming at it from this angle right here. Concave up and increasing. It's the only spot it can be. Okay, you know as we get to asymptotes, it's going to be close to one of those lines. It's going to be close to one of those asymptotes, right? You guys are okay with that? Okay, all right, cool. So it's close to one of those. Now here's an inflection point. That means it switches from concave up to concave down. And it's still increasing, which means I'm going to increase and switch over to concave down, so my graph is going to look something like that. Okay? No max, no min values, right? Which our table confirmed that.
Because it just keeps getting closer.
It just keeps getting closer and closer and closer. It never goes to one specific high value. Okay?